I recently saw the northern lights outside my house. This is a rarity. I live in the south of England, which is far lower than they normally show. The northern lights, or Aurora borealis, are high altitude illuminations caused by solar flares. I was unsure how this really works, so I did some research and I made this animation. Let's look into the science. The science behind the Aurora borealis. The sun emits a range of particles. Some of them are photons, which illuminate the days. Others are charged particles. These are kicked off from the sun in the form of solar flares. These charged particles travel through the vacuum of space until they collide with the Earth's atmosphere. So why can't I see the northern lights everywhere? That's where the Earth's magnetic field comes into play. The Earth's magnetic field is a magnetic field protruding from the Earth's core, coming from the North and the South Pole and then stretching out into space. The charged particles then collide with this magnetic field and get trapped. They accumulate in the field and then get funneled down to where the magnetic field enters the Earth's atmosphere. This is in the north, near the Arctic Circle, or in the south. With this higher concentration of charged particles coming through the atmosphere, they collide with oxygen atoms in the high atmosphere. This gives the atoms more energy, pushing the electrons up to a higher band. So this is unstable for the electron, so the electron naturally decays back down to the lower band, its natural home. During this process, the energy it received is then re-emitted as light. In the animation here, I've shown how it interacts with an oxygen atom. These can be found sparsely about 250 kilometers above the Earth's surface. When the electron returns to its normal band, it releases a red photon. This gives the aura its red glow. So where do all the other colours come from? Depending on what part of the atmosphere this radiation is affecting, it changes the colours. Under 250 kilometers above the Earth's surface, the oxygen atoms release a green or yellow photon. This may be due to the oxygen being in a pair. Around 100 kilometers above the Earth's surface, it also interacts with nitrogen atoms. Nitrogen makes up 2/3 of the Earth's atmosphere. These produce the other colours of blue, purple and violet. Of course, it all mixes together, so you get the just wonderful displays with all the different colours. So why are we seeing it more often and at lower latitudes? The sun regularly emits large quantities of these charged particles in the form of solar flares. These are correlated to sunspots on the sun. The sun follows an 11-year cycle where there is increasing sunspot activity during this time, peaking about now. So now is really the best time if you want to travel to see one of these events, as over the next decade they're going to become less and less frequent. Finally, how to understand the Aurora forecast. The Aurora forecast is measured in NT, nanotesla. This is a measurement of how the solar radiation is affecting our magnetic field of the Earth. A good way to understand this measurement usually ranges from under 50 to about 1500. So that's sort of the range you're looking at. Here's a quick guide to show how you should expect to see them. Under 50 is no activity. 50 to 200 is a faint activity, maybe on the very far north or south. Over 200 is you may be able to see it with a camera, say 2 to 400, and then over 500 you get to see it with the naked eye because it becomes really quite strong. The photos I've used in this example I took a couple of weeks ago, and the app says it was between 800 and 1000, so significantly stronger than usual.